right. Thank you for having a great introduction to me. Okay, thank you inviting me here. Well, let's get started. All right. Around 3 o'clock today, we might be a little bit sleepy after having a lunch here. So please enjoy the snacks. Thank you for serving the snacks and coffee here. And then relax and sit back, and then take some listening about my seminar today. So my seminar is talking a little about some audacious trial. So this trial means you can have a lot of some kind of error or kind of some failure or something like some big obstacle to overcome right there. But adverse weather conditions for autonomous vehicle and driving based on, you can overcome that object and challenges based on deep learning based perception and control. That's all my talk here. Okay, this is my brief introduction here. Then I work for Hyundai Motor Company and Samsung as well at the same time. After finish of my career in Samsung, I involved in the DGIST here, 2016. Yeah, at the beginning, so my autonomous figures starting is not that big right there, but with a small the car right there, I can start to detect the lane and object in the front. And then, so with those kind of the confidence, then you can build a real car and something like that. So we have a nicely detect the lane, even if the wrong condition and weather condition in there. But in the bright side of that one, so we may not have challenges in having a adverse weather condition in there. But anyhow, so, and more, you can talk a little bit about you can combine with the drone systems here to better getting the night path or safe free spaces, and then we can get the feedback from the drone or something like that. So my trial. And also, we need to combine with the infrastructure as well, right? So vehicle itself and standalone may not have smart enough, but drone and infrastructure or some pedestrian or something like a network, something like that. But this is my whole the way I did so far. But in this day, I'm looking for this kind of hold my talk and adverse weather conditions and the rain and darkness and sometimes the wet or slippery conditions in there. So we are trying to get over to improve the better visions and better tracking performance, something like that, in case of the adverse or some weather condition there. So here is my big challenges here. So the cruise system here, they got a permission from California government, 2020 something, but at that time, they got to permit that one. So the maximum velocity might lower than 30 miles, and their operating time is at the night time. But they may not, they will not allow on the highways at the same time, heavy fog and precipitations and smoke at the same time. But I heard that you may heard that the news, the cruise system had some big accidents. So when they are driving car, hit the ambulance in the last couple of months. So, but the patient in the emergency car, he or she has died. Then the government to take that permissions from the cruise. That was that story. But anyhow, so our challenge is coming up to overcome this kind of the adverse weather condition in there in the future. So Waymo and different kind of the autonomous company is trying to get over those kind of things, and particularly Tesla as well. Tesla are trying to get over this kind of challenges right now. Snow and ice, and defense fog, and rain, and more on the slippery condition there. So Tesla is trying to have a big test in China. So hopefully they can have a good job in launching the autonomous robot taxi right there. So they have a lot of they can collect a lot of some data set from China, and they can get over and they get a good kind of experience from China, and then Elon Musk can declare that around the August or October they can open that robot taxi, but it's delayed sometimes. But time is not that important right there. But the main thing is they can trying to tackle, and they can put a lot of the autonomous vehicle in real world. So not 100, not 200 robotics as well, but they can produce thousands of autonomous vehicles in the real world. And then, so they need to get over this kind of adverse weather condition in the future, I guess, right? So this is my whole small step to help them to get over those kind of very big challenges in there. So as you know, many kind of adverse weather condition here, right? Rain, snow, and darkness, strong light, and then storm hazes, right? Those kind of very challenges, the adverse weather condition here, then we need to nicely detect what's going on the vehicle, around vehicle, then based on that good perceptions. So we need to have better planning algorithm here, and then from that command from the planning, so the mechanical engineers need to operate the vehicle well, right? So this is my whole small studies that I done before. First one is the perception part here in weather condition here, and heavy rain condition here. But the mission is the land detection here. And second one is rain and snow conditions for the object detection here. Then, so we need to tackle the darkness. We developed the LuminanceGAN for getting over the different kind of light condition in there. And this whole part from perception field that I did before with my students. And the second part is control and decision here. When you have the very slippery condition on the vehicle, then how to tackle that one. And you can use the different kind of the deep learning neural network here right there. The first part is rain detection in heavy rain condition right there. So we have a lot of some blockages from the heavy rain. So in that cases, the sensor may not work properly in that time. So in case of having a heavy rain out there, so how can we tackle that one? So here. Then so here's our approaches to develop how to tackle this one. So evaluation framework by deep neural network here. So in case of heavy rain here, how can we collect the data and how can we evaluate how does the performance may be decreased in that part in certain area, and then we can collect data, and then we can take the learning process, and you can develop different kind of network model to better the vision performance. Right. So usually here's the ideas. You know, in case of having a small number of the data, and if you want to try to collect the good data in hard condition in there, it might be very dangerous, right? Then so we need to have a kind of better data without having some kind of action right there. So that's why we have some kind of the data set in simulation area here. So we have some scenes here, and we can generate some rain condition here. We can generate better real data for the learning to improve the rain detection algorithm here. Okay. So there are two types of approaches to detect the rain nicely. And traditionally, you can use the kind of image processing here. You can use the OpenCV. And next is deep learning network here to detect nicely the lane of the vehicle. So we have some kind of scenarios in CARLA simulator. Then you have the straight and then the curved lane here. You can generate that one. So we have synthetic rain signals here, and we have the condition here. Then we can combine together. You can have weather conditions, scenes a lot. But here's questions. Then how to make more realistic synthetic rain here? Here's a big question. So we need to guarantee this the synthetic image should be more realistic to evaluate, to learn on the network model. So then when it comes to talking a little bit about the how realistic it is, we can use the SIM here and PSNL. So we need to guarantee the number of the SSIM and PSNL to secure this the data set is very close to the real data. Then we can better the learning and validations and test the procedures here. So in order to get the realistic data, so we got some real rain data depending on the precipitations. So we have not many data about the precipitations, 15 millimeters power, and 25 and 30. So it is the real data from the government or something like that. Then based on that one, we can expand a little bit more the data set. So we have some 3-point here, and we can have extrapolations. Then in terms of the raindrops, we can correlate the precipitation rate in the rain here. Then, so in order to validate and learning, we can use the ultra-fast rain detection algorithm here. And we had a data set precipitations, and TuSimple and CuLane are the popular for rain detection algorithm data set here. Then, so TuSimple and CuLane, they have highway and urban, but we are trying to focus on highway first. Then they may not have rainfall amount here. So we are developed, depending on precipitation rate, we can get some data set by using this procedure here. Then, so in order to check out the learning model is if is it correct or not, we can use the pure pursuit algorithm here. So we can see this point might be distorted in case of having a high precipitation in there. So we use this tool here. Then, so I'm going to show you. First of all, we can use the traditional method. We can have OpenCV here. Then in case of the straight lane here, then in case of having 100 meters per hour here, and you can look at the lane detection performance might be decreased a lot. And there's a cover scenario here. Then without having a precipitation here, the lane detection algorithm pretty well. But in case of having a heavy snowfall here, heavy rain here, then kind of detection algorithm might be very decreased a lot. And then we try to for here. Let's see. Let's see. Okay, so in case of using a deep learning ultra fast lane detection algorithm here, then look at that one. So in case of 60 meter per hour second here, in case of 2 sim here, then so you can use that one like here. Yeah, look at that one. So yeah, this is the precipitation, the level here. Then ultra fast lane detection algorithm assume that those kind of the white, the dot seems like considering that the lane here, then they may not detect the lane right here. So that's why we consider that in case of heavy rainfall out there, the lane detection algorithm might be very decreased a lot. Then we need to improve those kind of performance in the lane detection here. Yeah, okay. Then here's the final result here. Okay, in case of a straight line there, so rainfall rate 20 and to the 100 here, then so this curve a little bit challenging than the straight here. That's the obvious result right here. Then here's when you look at that one, in terms of the rainfall rate here, then we use the ResNet 18 and 34 and 1 here. Then this kind of the decrease of the performance of the lane detection here, right? But this is the CU lane. But CU lane comes from urban area, so we may not use that one. So you can remove the word here. Then only focus on the highway here. So we are developing here urban area here, but not this time. But so in order to usually there's a drop performance of lane detection here. So based on different kind of approaches, for example, the domain adaptation network or style transfer network, something like that, we can improve a little bit. And in spite of having the heavy the rainfall in there. But we are doing this job to improve lane detection performance in this day. So in case of having a good result from that approaches, I'm going to, I love to give it one more seminar in the future, hopefully. All right, next the job is to improve object detection performance in case of heavy rain and snow here, okay? Then in previous research here, there are some of the study about to detect objects in case of rain here. But so in our trial, so we can have a classified how heavy, how big precipitations here and snow and the rain at the same time. So this is the different approaches rather than the previous study. So we use the YOLO and we use the T-SIT to generate kind of the snow and rain, the fall images here. And we use the KITTI dataset first, then we translate into the cloudy and dark based on some experiment here. Then we have rainfall here and snowfall at the same time. So we generate that one. We generate the synthetic data based on rain and snowfall here, and including some cloudy and dark at the same time. Then we check the time to collision performance here. Then we measured how the performance might decrease in case of having a rain and snowfall, and at the same time. Okay, and we compare the AP score and TTC here. Okay, as we said earlier, we can use this kind of approaches here to classify how precipitation is increased or decreased here based on the experiment here. But the snowfall, a little bit difficult to classify how much it is. So we surveyed a lot of the reference here. So we found this kind of the equations here. Snowfall rate comes from snowflake lake density and diameter and velocity, rainfall rate here. Rainfall rate is involved in this snowfall rate here. Then this comes from that reference here. So we found a kind of density and diameter size and so on and so forth. So we finally correlate from precipitation into the snowfall rate here. Then we generate normal conditions and rain and snow. Usually when you have precipitations, the sky might be cloudy, or sometimes it can dark here. Then we change our data set into cloudy and dark at the same time here. Is that similar? But let's see here. Depending on that situations, the normal and snow and rain and snow and in the cloudy and dark here. So then we checked out how much of the DTC might be decreased depending on each level of precipitations and rain and snow here. So here's the okay. Okay, this is score. Yeah. It's a real data. Look at that one. So in the 0 and 50 and 100 here. So look at the TTC here. TTC might be 6.3, 4.4, and at the first seeing the front of the vehicle is detected here. Then this one is a little bit slower, 3 point or something. Okay, and gradually and decrease the TTC performance in case of having a snowfall and the rain. In case of having the cloudy and darkness here. You can have questions. Is that the real or is that very similar to the real conditions? So we are supposed to, in the futures, we are trying to get a validate, which is the same as the real condition in there. So, but those trial, it might be a challenge in the futures, but we are trying to get a validations, the real to the synthetic that at the same time here. Okay. And next trial is to, in case of the different kind of the brightness or looks, luminescence, depending on that darkness, you are trying to check how much the lane detection or depth estimation might be decreased or not. That's another challenge trial to overcome those kind of the darkness and autonomous vehicle environment here. Yeah, we are usually at nighttime and foggy environment. There are not much data set here. Then we are trying to generate those kind of the data set depending on different kind of brightness or darkness here. Okay, mostly about 86% data set comes from the day and small number of the data set from the night right there. Then, so we are trying to generate the data set from the darkness or the light here. But here's another big question. In order to generate the data set from darkness, so most of the generation model may not have specified darkness. So it's only this kind of dark images. And also they can have more the artifacts in there. So we need to tackle two things. And how dark it is, and how can you handle those kind of the artifacts in generating those kind of the data set from the night or something. Then you can use the Y value here, luminance value here. So depending on Y value, we have controlled the Y value, the darkness level here. So we face into the big questions. How can we define the brightness here? There are two types of darkness to define brightness here. Illuminance and the luminance here. So you look at that one. So we can call that luminance here and illuminance. Reflection, that light, you can call that illuminance. So we are focused on luminance here. How from the source, we can use that brightness by using the luminance here. Okay. So in terms of luminance here, so we found that the good definitions, the methodology to define how dark it is. So YCB CR value here. So CR and CB is corresponding to the blue and red here. So we are more focused on the Y value, luminance here. Then, so we are trying to clip the Y value to define the darkness here. So here's Y value here. We are more focused on the Y values here. Then, so in Korea, there are a lot of some dataset centers, AI hub here. I think that you may have, you can generate a lot of the data set. You can connect with the big data set in the United States. But in Korea, we develop a lot of data set from Korea. So we have this kind of, depending on the time, depending on cases, there are many kinds of the CCTV camera in Korea. So we collect this one depending on the time, from the morning to the night here. Then, so we measure the Y value depending on the time here. So normally, nighttime is the Y value is 9 to the 10, or 100 here. Daytime is 110 and 130 here. Okay, this is one good finding. And then urban area, this highway here, from the day to the night here. So we have different kind of the scenarios here. Then, so highway, they may not have lights on the road, and you can have the smaller value of the nighttime luminance value, Y values here, and from 50 to 80 here. So, okay, so you can look at the number right there in the following. Yeah, here's all my procedures here. So in the daytime, good data from the KITTI here. Then you are trying to generate the night images from the real, adding some algorithm. So depending on the darkness, Y value. You can control the Y values. But normally in GAN model, they may not produce the night images depending on darkness here. Just only having artifacts as well. So in my trial, to classify that images here. Then we add some attention algorithm here, and finally we get this kind of images here. Okay, here's a self-attention here to minimize. Original data here, if you use a cycle GAN, and you can have many kind of artifacts here, and distortions at the same time. And so cycle GAN plus Y model here, and this small number of artifacts here. It's improved a lot. And also we can add self-rotations and Y values at the same time. We can better. So here's a Y value, kind of the much dark. Okay, so we can have different kind of the darkness in whole the environment here. So we can generate different kind of the darkness here. Okay, this is one of the thought which positions of where the self-rotation networks should be located, and the after residual block will be better than others. Okay, this is the full cost function, and we are focused on this one. Y control loss value. We're trying to classify how dark it is, depending on Y value. This B is the bright target value here. We can call Y values here. Then let's look at that one. So if you're trying to kind of the 10, so a little bit more darker, and lighter, depending on B value, we can control that one, right? From the day to the evening to the night, and very beginning of the dawn or something, you can have different kind of the darkness value in the images here. So we proved that one. If you're trying to control this B value, Y value here, and we have the 50 and 20 and 10, very nicely you can control the darkness by changing the B value here in the learning process here. Okay. Then we can generate night images which has a different kind of the darkness. Okay. Then we put this value into we can compare cycle GAN, Munich, and DRIT plus DZIT, and we can have that this model here. Then we can use the BTS here for depth estimation. But now, this is the last year's study, so now we are trying to lane detection and objective at the same time. But this is a depth estimation performance. We compare that one. If we add the classified darkness images here. Then if you look at low images here, so if you use the cycle GAN, and there are different artifacts here, and DRIT and different kind of artifacts, they can have only one value of the darkness here. But if you use the B value, different the Y value and darknesses, and you can control the darkness of the night here, 10 and 20 and 30 and 50 here. Okay, we can mix together, combine together to learn the model, to train the model here. Okay, this is a patent. So we already issued a patent in Korea and United States as well. Let's see into here, a very similar procedure. So we can have different kind of the brightness level of the images here. Then by using the images collected by our approaches here, then we tested how our model is working properly to improve the depth estimation performance here. Okay. For here, so usually this value is SQRel RMSE. If you look at that one, so usually with Y value is 50, and we use the half of the value is coming from this one, half value of the normal data. So we combine it together. So then if you use the Y value 50, and there's a huge improve rather than the model here. Okay, this is a good result, and we are apply the good journal, the site here. We are reviewing right there. So we had second round of the rebuttal for the publication in the future. Okay, next part is a control part here. In case of the low friction here. So you might be the expert in the learning software engineers. So one of the guys in my lab are measuring in mechanical engineering here, and they are trying to design the control algorithm to improve the tracking performance based on the vision right there. And they can derive the motional equation of the vehicle, and they can control the tire, and they can control some suspensions, and they can control the vehicle. But they can apply some deep learning algorithm here to estimate, to improve the direct model. Okay, that's one of the approaches for this study here. As you know, so it is very challenging to perceive the object and lane. But for the real controlling the vehicle and those kind of slippery conditions and wet and those are another big challenge to the autonomous vehicle, right? Obviously, and right here. So in case of having this slippery, okay, here is the obstacle here, and if you're trying to avoid the collisions here, we need to adjust the vehicle velocity or some kind of steering or braking, and at the same time, then we need to secure the stability of the vehicle. That's the key missions for the mechanical engineers in the future. Yeah. So this whole process here, then we are trying to develop model predictive control here based on LSTM or a GRU or something. This algorithm here is vehicle, then MPC algorithms here, then slightly mode controls here, and in order to adjust the torque of the vehicle. Then in order to estimate those kind of the tire force, then we are trying to use the LSTM algorithm here. Okay, this is a bunch of equation of the dynamics to derive how the vehicle is working properly, and that's those kind of the function is required to generate optimal the control input from that maneuvering here. So we need to derive first. Then Fx and tire force, longitudinal and lateral tire force is very essential. That should be the measure that should be estimated by using network model here. The MPC model to obtain the optimal control, the steering, or sometimes we need to generate the torque of the vehicle. Yeah, torque generate, lateral here, then torque and steering at the same time. Okay. Yeah, then, so as I said earlier, in order to obtain, estimate tire force here. Tire force is very essential to estimate, to get a optimal TI torque, optimal steering angle. Then based on the LSTM estimator, we are trying to estimate tire force, longitudinal and lateral force. But so in order to get some data set for the learning, so we use the CARLA. CARLA is a very typical program to generate the data set. It's very close to the real data, and they had a lot of some good realistic data set into the simulator here, and tire force and suspensions and the vehicle, different kind of condition in there. Then hopefully this kind of procedure is very realistic to the real vehicle here. And we generate easily this kind of slippery conditions here, and we can stick there. So we can get some data set from car sim here. Then we can generate car sim. Based on those kind of data set, we are trying to estimate longitudinal lateral type force here. Okay. Then here's a simulation here. In case of having the slippery conditions when they are turning the vehicle, then we compare with Kalman filter. So Kalman filter is pretty powerful tools to estimate the type force, but we compare two things. Obviously, LSTM is a slightly better than the EKF, and with a small number of resources using for estimating the type force as well. Okay, here is the real simulation here. And in case of the lone view here, okay. So if you use the LSTM is we can have smaller kind of divergence here. It means that it is a little bit more stable than the vehicle using the EKF or something like that. Okay. Okay, this is one of the study here. And finally, so we are talking a little about the optimal algorithm. So MPC is require a lot of computation here, and also sometimes it might be unstable. The MPC itself may have some unstable because they have a lot of computations in there when they are driving the car. So we are trying to tackle those kind of reduce the computation resource and we secure the stability of the vehicle at the same time. This is another study. Okay, it's very similar cases here. So as vehicle engineers, we need to secure the vehicle safe in case of very hard condition in there. Okay. Okay, here is the block diagram here. Then, so in order to control the torque here, then we have sliding mode control here. And in order to minimize the computation resource, we use the low rate functions of the MPC here. Then this is for reducing computational load here. And in order to secure the stability of the vehicle, and we use the SMC here, non-singular SMC here. Usually traditional MPC algorithm here, we use this kind of optimal cost function here to generate that one. Then require a lot of the computation here. So then in order to reduce the computation loss here, we use the low rate function here. Then, so in order to minimize that one. At the same time, as I said earlier, in order to secure the stability of the vehicle, we use the okay, this is another low rate function here to minimize the resource of the MPC algorithm here. And also to secure the stability of the vehicle, we use a non-singular terminal sliding mode controls here, depending on alpha and the data values here. Okay, so first of all, the MPC algorithm is for to improve the tracking performance here. We need to compare the tracking performance at the same time. You know, look at the, here's the reference here. Then if you use the TMPC is 4 means the horizontal, estimate horizontally should be smaller, and then it's a little bit safe or lower computation here. Then, but the tracking performance is pretty poor. But in case of the 35, horizontal estimate horizon here, TP here, prediction horizon here. If a large value of tracking performance is pretty good, then so we apply for logarithm function here. Tracking performance is pretty similar with the traditional MPC 34 here, right? But here, in terms of tracking performance here, it's much way better than the traditional MPC algorithm 34. Prediction horizon 34, 35. 35 means it uses a lot of resource for computation here. But logarithm functions is a lighter computation time, and so it's better tracking performance. PY is tracking performance here. Okay, so in terms of the stability here, we need to talk a little bit more about Hessian matrix here, and minimum eigenvalue of the Hessian matrix and maximum of that one. So if you smaller value of that one, and our control algorithm is more stable here. So in terms of control number here, then so in case of a large number of prediction horizon and computation number is pretty high, it means that it easily unstable in the real experiment here. So our target is to minimize the condition number, even if we having a large number of prediction horizon here. So then in terms of tracking performance here, traditional and logarithm experience would be much better than the others. So this is our proposal here. And depending, in case of having a low, the mu condition here, and tracking performance is better than other performance, and then condition number is smaller than others. It means that it might be a little bit safer at the stable than any other. So we can have two types of advantages by using the logarithmic exponential MPC functions here. And moreover, so we need to measure the computation time at here. So TMPC, traditional and logarithm function, logarithm exponential function here, we can have smaller number of computation time. So we had achieved the two things: a smaller computation time and more secure, more stable than the traditional MPC algorithm here. So we compare the three control algorithm here: area MPC plus non-singular SMC here, then fuzzy control and conventional SMC here. So if you look at the tracking performances, the area MPC plus NT-SMC is way better than other ones here. Okay. In terms of lateral displacement errors here, if you look at the proposal here, very smaller than any other approaches here. Then we accomplished to the key things. Okay. We can achieve the three things: better tracking performance and safer and stable, and the smaller number of computation here. Okay. Here's the final result here. Then similar one, depending on the speed here. So we have the better algorithm here. Here's the proposed one, and smaller tracking performance here. smaller error for the tracking here. Okay, in case of having the slippery condition in there, so it also had a good performed well, and proposed the algorithm here and nicely tracked well without losing some stability of the vehicle in there. Okay, proposed one is a yaw angle tracking performance is pretty good. All right. This is all I have today. So in terms of this part is not that fully developed here, but we are trying to tackle more nicely and successfully, and we are ongoing process to help the autonomous vehicle algorithm in case of in weather condition in there, and in case of the control error part here, then in order to secure the vehicle stable in case of having a very hard maneuvering condition in there. And those are the homework in the future to contribute the algorithm in this area here. Okay, I'm going to thank my ASL members here. I have 9 PhD students here and 6 the master here. All right. Thank you for listening to my talk today. Thank you.